So, great pleasure. You already heard Dr. Jarrod Miller. He's our extension agronomist. Dr. Amy Shober, Amy, and Dr. Leah Palm-Forster. I think you all got those of you that participated in the corn nitrogen modeling. So, turn it over to you.
All right, thank you, Mark. So we're going to use this stop to talk about some of the work we're trying to do in variable rate applications and doing a better job of mapping soil variability for nutrient application. You can pick up this first poster, Shawn. So one of the tools that we have here at the research station is we have a Varus electrical conductivity piece of equipment, and we have an EM38. So on the left side of this poster that's colored in yellow and blue, it's an electrical conductivity map of your soil. So soils conduct electricity. If you think about CEC, that's absorbing cations. You got calcium, magnesium have positive charge. Your soils have a negative charge. So you already know your soil can conduct electricity. That's how it absorbs nutrients. So if you can take a piece of equipment across there, you can at least measure that part of it. You can possibly measure CEC. Organic matter has a charge. You can measure that. Water, of course, we all know you don't want to stand in water during an electrical storm. Water also conducts electricity, and so do salts. So if you add a fertilizer to your soil, you could actually possibly measure the conductivity of that salt through a piece of equipment. So the Varus that we have here has these coulters that go in the ground, and they send a current across, and they can measure a shallow EC and a deep EC. So you can measure these soil layers. But it also has, this Varus has a pH meter on it. And as it goes across, it scoops up a piece of soil, and it measures the pH of your soil. So a question we had, and this is back in 2019, that Shawn was carrying around is, when you think about liming your soil, if you've looked at the lime recommendation, there's two pHs you need. There's the pH of your soil, which you want to change. If you want the pH to match your crop needs or the possible micronutrient concentration in your soil. But to add the lime, you have to consider buffer capacity. Because your soils have acidity absorbed to that CEC. You're never going to have 100% base saturation. That's not a good idea. So if you have a soil that has 80% base saturation, it means it has 20% acid on it. So when you lime your soil, you don't just lime based on the pH that you read, you also lime based on its buffer pH or its buffer capacity. So what we were hoping we could do with this Varus is, if it's measuring CEC, if it does a good job at that, can we use that CEC to correlate to buffer capacity? And then can we use the pH of the Varus to possibly create a variable rate map of lime application? So there's going to be some issues with that. I can show you different maps. If you run that Varus across the field after a rainfall, you measure water. So it doesn't matter what the CEC of your soil is. It doesn't matter what the clay content is. If you have a depression on top of a hill, it's going to measure the water content. So you can have variability. There can be residue issues. So the map might not work well. And also, that CEC is going to be related to the mineralogy of the soil. So it's not an exact way to do it. So what we did is we mapped the field, and we went out and we took about 12 samples per field. We did 2 fields, to see if we can match the CEC to buffer capacity. In one field, we had a really good linear correlation between the buffer pH of the soil and the CEC. It worked really well. In the other field, it was a little wonky. It didn't work quite as well. So then what we did is we gave a recommendation to a variable rate applicator to apply lime across that field. So the first map on here, you can see some stratification between high and low pH that was probably due to past lime application. And you can still see some stratification after we applied lime. So the target pH was about 6, and we got most of the field to wrap around that. It went from about 5.5 to 6.5, so we got it within a range, but it wasn't a perfect application like we were hoping to get, because we still have to do some more work in looking at whether we also have to consider mineralogy or how well these maps do. But this is one way that you can map a soil. So even if you don't use that for a variable rate application, you can use this to target soil sampling. Because if you look at an NRCS soil map, it's as accurate as they could get it by walking across a field as fast as possible to dig down and map. But if you look at all this, you can see a lot of variability across that field. And you can match that up to satellite imagery, to yield maps, to get a better idea where you could soil sample. Another project that we did last year that we still have to get the results from, you can carry this one now, Shawn, is we did a grid sampling project. So quite a few you do grid sampling. So I'm sure you've looked at the results, and one of the questions that they have that they've looked at over the last 30 years is how dense do your grid samples have to be? And we used our Warrington Irrigation Research Farm, where we can go across there and sample on about 1/4 acre grids. And then in some cases, what we did is we deleted points out to get it up to 3-acre grids so we could look at how accurate these maps are. Most of the recommendations across the country are no more than 2 acres per grid sample, and you get a lot better resolution if you use 1 acre across there. So if you look at these maps, you can see on the left side, we have the very dense 1/4 acre grids. It's about 400 samples, very expensive, but incredibly accurate map of CEC. And the second map is if you knocked it down to 3 acres, and it's not quite as accurate. We also have the pH, and then in blue here, you can hold this up right in the middle here, Shawn. This blue map right here is actually the lime recommendations that James did and put out this year. So we did a variable rate lime application based on a really dense grid sampling, and we can come back and see how well we did with that versus using the various applications. In the past, because I think things should be easy, there's another way you can precision soil sampling is do by management zones, which you could use a Veris map to do that, or your yield map. You look at where you have high and low yielding parts of the field, and you group those together, like the CEC. You can say, okay, I'm going to treat this as one zone, and this as one zone, versus sampling all these points, which to me has always seemed easier and straightforward, and it should match your yield application. However, because we sent these to the UD lab and grant money, we went across there and ran all the micronutrients. And what was really interesting as a soil scientist to see these results was how different the micronutrients were across this field. So you have zinc at the bottom here and manganese at the top, and all the micronutrients varied a lot across this field. They didn't match, which I would have thought in some cases that where you had high zinc, you might have high manganese, but there's a lot of differences. So I think if you are going to do grid sampling, at least once across the field, if you're already going to do all that work, you should run the whole suite of nutrients, because in most cases, a lot of the work's been done focuses on phosphorus, and potassium, and pH. But they might be missing, especially on our coastal soils, a lot of this variability. So our lime recommendations, if you were to try to get the same pH across this field, you might find that one part of the field now has a zinc deficiency, and another part of the field has a manganese deficiency if you try to get it to all the same pH. So there's some work that we can possibly do with these maps in trying to figure out whether our lime applications don't have to be just based on buffer pH and the pH of the field, but also the micronutrient concentrations across that field and how well we can match that up. So that is, we've just put these out this year, and a variable rate potassium, so we'll be able to come back and see how well we did across this field and then expand it across the region. So if you guys don't have any questions about this right now, we can move right into Amy, who's going to talk about some of our work with using sensors for nitrogen application.
Thanks, Jarrod. Shawn's going to pass out some of our yield responses so you can take a look at what we've seen this past year, but I'm going to talk a little bit about a project that we have ongoing with the University of Maryland College Park and Penn State University, where we're looking at in-season nitrogen management tools. This is part of the CIG's recent program where they're looking at on-farm research projects that are designed to increase the adoption of practices that have already been shown to work in the field. What we know is that there are barriers to adoption to new practices. So their idea with this program was to put out a lot of field trials with farmers, and hopefully they would see what is working and what is not working, and it would increase adoption. But one of the things that we found with these field trials is that they can be pretty cumbersome and they can take a lot of work. Thank you to our grower cooperators who participate in these. But ideally blanketing the entire Chesapeake Bay region with these nitrogen rate field trials would have been a pretty big undertaking. So what we've done is we've done these traditional field sites on about 6 to 12 fields across Maryland, Delaware, and Pennsylvania. And then, as you'll hear a little while, Leah Palm-Forster and her group have actually designed a behavioral economics study that complements the work that we're doing in the field to understand really what is it that's driving people to make these decisions about adopting these tools. So I'm going to take a moment to talk about the field research that we have, primarily talking about the work that we've seen since the last year. What we have done on our grower cooperator fields is we've actually put out strip trials where we put out 4 times 6 different rates, each replicated 4 times, where we put a single application of nitrogen up front, and then we use 6 rates at some percentage from 0 to 120% of the recommended in-season nitrogen rates based on your yield goal. The idea here is to generate these real yield response curves for the fields. Those are the papers that you're seeing, those little yield plateaus. That shows you what we found in Pennsylvania, Delaware, and Maryland. Once we have these response trials, we can actually compare the yield that we obtained that would have been the maximum yield for that field. What is your response? What was the N rate? What was the maximum yield? And we can actually run a variety of different tools with the same data up into that point, and we can compare how those tools' recommendations came out with that actual yield response. So Sapna, who's a postdoc on this project with us, can show you a couple of these tools. This first one is a handheld green seeker. Some of you might have heard of the green seeker before. It uses multispectral imagery to figure out essentially the greenness of the crop. A similar thing we have, do this one. We have a multispectral camera on our drone, so we can do a similar type of activity, whereas with a handheld or an equipment-mounted sensor, you would have to drive through the field or walk through the field. With the drone, we can actually fly over the field and get multispectral imagery of those fields. And using these indices, we can actually make a recommendation around the time of V6 as to what the rate that you should apply with your nitrogen is. The way we do it with these multispectral type products is that we have to have a 0 or no end strip and a very high end strip, so that we are comparing a crop that doesn't look great to a crop that's had plenty of nitrogen out on there. Then we also have more simple tools like PSNT and chlorophyll meters, and then we are also comparing to some dynamic nitrogen models. So something like ADAPT-N or Climate Field View, where they're taking information about the soils, the weather data up to the point of the nitrogen application, and a variety of different environmental factors up to the date of application into effect to determine that nitrogen rate. Once we get the yield responses, we can see how those other tools compared. Right now, I just have the information from our drone-based sensor base, and we had a site in Pennsylvania, and Delaware, and Maryland where we did this. And on the other side of your paper, it gives you that information about what the recommended rate would have been for that particular site, and then what our nitrogen rate at the yield plateau was. So essentially the maximum yield you could have gotten for that field, what was the nitrogen rate that we applied to achieve that. And then we also calculated based on fertilizer price what your economic optimum nitrogen rate was. And if you look, the Pennsylvania one lined up pretty well, where we had a sensor-based N recommendation of 142 pounds per acre of nitrogen, and the N rate that we reached the plateau was 148. So we were really close there. But then if you look at the Delaware site, our sensor said you need 72 pounds per acre, but our yield plateau didn't happen until 282 pounds per acre. So we were like, what happened here? We don't know. Well, it turns out that we didn't have a very good N-rich strip in that particular field. So our 0N and our N-rich strip didn't give us enough data to help us to make that recommendation. So we found that you really need to have those good data to guide that nitrogen application rate. And in Maryland, it just turned out that that site wasn't responsive to nitrogen, and sometimes that just happens. It could be that site history, it could be the soil's really good, it could just be that everything lined up in that particular year. And on top of that, we had a student, Jeremy, who he also did a little bit of extra work. Some of the things about the NDVI and these other sensor-based technologies or indices that we can calculate based on these wavelengths of light is that they only work until the canopy gets so big, at which point they just can't tell you it's gotten any more biomass because the whole thing just looks green. So what we did is we said, can we improve upon this by taking measurements of plant height? So Sapna and Jeremy have gone through the field and they have actually used this measuring stick to determine how tall the plants are in the field. You can imagine that's not a really easy task, right? And then we've also used a handheld meter over here, which she'll pick up or somebody will pick up, a leaf area index meter. So it's essentially giving us a measure of how much leaf area we have in the field. And our hope was that we could use this or a method of calculating plant height with the drone to give us a little bit more data that would help us to tease out these additional accumulations of biomass that happen, say, after R2. What we found is it only marginally increased things, and what was interesting is that we found that there's a really significant problem with the drone-based estimates of height. What happened there is that at each individual site, there was actually pretty good correlation between the height that we saw and the height that we measured. But when you compared across the 3 sites, it was completely different. So it's very site specific, and we need to kind of tease out a little bit of more information to try to get this to be something we can apply across a wide range of area so that we can use that height measurement without having to go in the field and do it. So we'll be doing another set of field trials this year, and then we've coupled that with the behavioral experiment, which some of you, thank you, participated in this afternoon, and which Leah is going to talk a little bit more about at the next stop. I think that's all I've got, if anybody's got any questions.
Any questions? Quiet today. Listening. All right, that's good. All right, let's give our speakers a big round of applause.